Elimination reactions fall into two basic categories in this chapter. So the first is an E2 reaction. It's a bimolecular elimination. And the other reaction is an E1, which is a unimolecular elimination reaction. So for an E2 reaction to occur, we need to have a base. And the base needs to be a strong base here. So we have to have a strong base. And we'll see if we have a big bulky base like T-butoxide, this can promote E2 over SN2. So it turns out that E2 and SN2, they're going to end up competing with each other. Now during the course of this mechanism, the halide or just the general leaving group and the proton that's taken off happens simultaneously. So we say sometimes in organic chemistry, this is a concerted reaction. It's one step. Also, the reaction has three products. So you get HB, you get an alkene, and the leaving group. And because of that, heating this reaction will favor elimination over substitution, because the T delta S term for your Gibbs energy is going to have more of an impact with three products. Also, we can favor E2 over SN2 if we use a polar protic solvent. So solvating those anions decreases their reactivity towards SN2. So let's look at the mechanism here. So we're going to start off here with this. So we'll have a carbon here with 3 H atoms on it. Then we're going to come over here to a second carbon, and we're going to put a leaving group on here. And we'll throw this here as an H, and then we're going to put an R right here for right now. All right, so just to highlight a couple things, the H that's going to be lost is at this position. So let's just look at this a little bit. So here is our LG, that's your leaving group. All right, and here's the H atom that's lost. So this H. So the type of base that we're going to use here is a strong base. So one of the common ones that we'll see is hydroxide. So a couple of key things to mention to you about this. So the H atom, right, and the leaving group must be anti to each other. So remember, we could see that anti-arrangement when we look at like Newman projections, for example. And there's also some labeling that we can label here. So this position, this carbon here, that carbon we call the alpha carbon. So let's label that alpha. So then any of the carbons that are adjacent to this would be the beta carbon. So there's a beta position here, and I've kind of limited us right now to our choice of products by just putting an R here. So that's also a beta position. Now, if there were any H's on that R group, then you could get an elimination product from that position too. So the first step is we're going to come around here and we're going to grab this H. That's the first arrow of our only step. It's a concerted step. And then what happens is the electrons here are going to come over and form an alkene at that position. And then we can't leave it like this, because then you'd have 5 bonds to this carbon with the bromine atom. So we're going to come over here and we're going to kick off our leaving group. And that's it. Seems pretty straightforward. Turns out there's going to be some stereochemical and regiochemical, I guess, outcomes that we have to investigate here that make this a little bit more complicated. But our product here would be, in this case, H2O. Right, that's like your HB, essentially. And then you're going to have bromide. Right, and then we will have our carbon-carbon double bond here. And H atoms. Here, R group up here, and an H down here. Again, to point out here, don't forget we have 3 products, right? So increasing the T delta S term will favor this reaction over SN2. Okay. And again, here is our alkene. So conveniently in this chapter, we learned how to do substitution reactions. We learned how to make alkenes. And then the next two topics typically in an organic class would be reactions of alkenes. And that's what we're going to cover in our next chapter. The rate law here depends on the concentration of the substrate and the concentration not of the nucleophile but of the base. So remember, a base is required because if you recall, bases grab hydrogen atoms. So when we make a bond with an H atom, we are a base. And then the overall order of this is second order. That's where you get the E2 part coming into play. Now this reaction is regioselective. So it turns out that substrates, the reactant, can have more than one type of beta carbon. So we're going to first take a look at kind of some basic stuff, and then we'll look at all of the options that we have that can lead to different stereochemical outcomes. So let's first start off here by looking at this reactant. So let's just put an H right here. We'll write that out. Put a bromo group right here. And let's look at this. So let's look at this reaction, and let's treat this with hydroxide. So I want to point out to you guys as we look at this, this is a secondary alkyl halide. So here's how we handle this. So what we do is we recognize that is the alpha position. And then we said beta to this, if there's an H there, has the potential for being lost. So we have a beta position here. That H could be lost. And then at this end, we have a beta position too. And I want to write this out. So here we have a CH2. And just for the sake of putting H's in and keeping track of things, here's my other H there. So that H has the potential to be lost also. All right, so let's see what happens here. And let's label these things. Let's do this. Let's call that beta 1. And let's call that beta 2. And let's look down here at the E2 at the beta 1 position. So if we're putting our arrows in, we'd come over here, grab that H, come down. That would be our alkene. Right? And then we kick off our bromo group there. So this would lead to that H still stays there. And then we would have a double bond right there. Okay. That's outcome number 1. So let's take a look at the other choice. Right, so on the other side, we're going to draw this thing out. So 1, 2, 3. I'm not going to draw at the beta 1, I'm going to leave that as just a line there. And then we have an H here, and then our bromo group right here. Right, and then same thing happens here. Here we have hydroxide. And now again, so there's your alpha. Here's our beta 2. That was our beta 1. We already did that. So beta 1's taken care of. Let's look at E2 at the beta 2 position. So arrow flow concept is the same, except we're just grabbing a different H here. So we're going to come over and grab this H right now. So we're going to swing over there, grab that H, plop these down, and then we're going to kick off the bromide here. Okay, so now what we're going to get here is this. All right. So there's two products that we get here, right? Now, let's talk about which one might be preferred. So one of these actually turns out to have a different degree of substitution than the other one. And I want to take a look at this next little page here and talk to you guys about this. And I want to figure out how we can determine what the major product is. We're going to come back and revisit this. So what we're going to do is this. I think it makes sense. Wouldn't the product that's the most stable be the one that's preferred? Right? And that's kind of what's happening here. So let's take a look here. So it turns out that the number of carbons directly attached to the carbon double bond is called the degree of substitution of the double bond. So let's take a look at the situation up here above. So here's the way you deal with this thing. There's a carbon, here's a carbon, and you're connected to one carbon off of that carbon-carbon double bond. So we call this monosubstituted. All right, now the delta H of hydrogenation, what is that? Well, so what happens here is that you can take an alkene, right, and then you can add hydrogen to it. And we have to have here some type of catalyst. What you end up forming, though, is an alkane plus energy plus heat. So here we have something that's hot, right? We can measure this. And that's what we're measuring right here. The higher this number, right, or the more negative this number is, it means that the double bond is less stable. So monosubstituted, 30.1 kcals. If we come over here and look at disubstituted, right, here's a carbon-carbon double bond with 2 R groups off of it. Right? We could have done that a couple of different ways here too, right? So we could have done it like this also. That would be disubstituted. Right? That has a delta H that's a little bit lower than that of a mono, 28. Trisubstituted, you can see the pattern down here. Here's our carbon-carbon double bond, and you have 1, 2, 3 carbons sticking off of our carbon-carbon double bond. This takes you to 26.9, and then tetrasubstituted is the most substituted that we can get with 1, 2, 3, 4 different carbon groups. Our carbons attached to our carbon-carbon double bond. So most stable at 26.6 kcals per mole. So let's come back here and let's take a look. So of these two, let's look at this guy first. So this guy right here, right, there's your carbon double bond, and you're connected to 1 carbon here. We don't care about what the carbon's connected to. We just look at the number of carbons that's directly connected to kind of like that equal sign that's your carbon-carbon double bond. So this is monosubstituted. Okay. And then we take a look over at this fellow right here. What about this guy? All right, well, it's not too hard. There's a carbon, there's a carbon. We have 1, 2, 3. So this is trisubstituted. So trisubstituted versus monosubstituted, this is more stable, and therefore this is our major product. We call this the Zaitsev's product.